So we start with Newton's second law, and remember it's F is equal to ma, and what that tells us is that for every action if a net force acts on an object, the object will accelerate in the direction of the force. I'm going to rearrange that, and I'm going to write the acceleration as the subject. That acceleration will be directly proportional to the net force and inversely proportional to the mass of the object. Calculate the horizontal and vertical components of this tension. It's 100 newtons at 60 degrees. So this is my vertical, that's my horizontal. Horizontal is adjacent, the vertical is opposite. So horizontal is going to be 100 cos of 60 degrees, because cos of 60 degrees is going to be equal to the adjacent over the hypotenuse. So that turns out to be equal to 50 newtons. And that's to the right. And then the vertical over there is going to be the opposite side, so it's 100 sine 60 degrees, because sine of 60 degrees is equal to the opposite over the hypotenuse, and that turns out to be 86,6 newtons to the, I'm lying, upwards. Calculate the frictional force acting on the sled and the parcels. Well, friction is acting against the motion. We do know that the force resultant in the forward direction is equal to the big force, which is applied, minus the frictional force. So the resultant force is going to be 25 mass times the acceleration of the system is equal to the applied force to the right, 50, minus the frictional force. So I can work out the frictional force, which by some coincidence turns out to be 25 newtons, but not because the resultant force was 25 newtons, it's just a coincidence. The next thing we need to do is calculate the magnitude of the normal force. Now, the normal force is a tiny bit more tricky in the sense that it's got quite a few bits and pieces that are acting. So firstly, we know that there is no motion in the vertical plane, which means that the weight of this particular sled, which is, well, let's do that, weight or force gravitation, is equal to the lifting force, the force applied upward, because we've got one of those, plus the normal. So I'm going to go 25 times by 9,8 is equal to this 86,6 plus the normal force. The 25 by 9,8 is going to be 245, and therefore my normal force will turn out to be 158,4 newtons up. The next thing they want us to do is the coefficient of kinetic friction. So FF is equal to mu Fn. Frictional force I've just worked out, 25. Mu I don't know. Normal force I've just worked out. 158,4. That's a 5. And when I rearrange that, I land up with 0,16. We've now got a labeled free body diagram. I'm just going to make this person the free body quickly. That's its weight, or force gravitational. Gravitational force. Then there is a force acting up the slope that's holding Dane in place. That is a frictional force. And then there is a force acting by the slope at 90 degrees to stop Dane disappearing into the slope, and we call that the normal force. Calculate the magnitude of the gravitational force on Dane. That's the simplest part. That's the 80 kilograms multiplied by 9,8. So it turns out to be 784 newtons. Easy. Calculate the magnitude of the normal force. Now we have to draw this diagram. Watch carefully. It's gravitational force acting down. Normal force pointing towards top right. Frictional force pointing towards top left. We've got a 90 degree over here and we have got 30 degrees between the normal over here and the gravitational force. Then the next thing that we're going to do is we're going to say, this is my adjacent side, this is my opposite side, and this over here is my hypotenuse at 784. So if I'm interested in the normal, it is my adjacent side, so it's going to be cos. So I will say that the normal force is equal to 784 cos of 30 degrees, or cos of 30 degrees is equal to the adjacent over the hypotenuse. That turns out to be equal to 678,76 newtons. Calculate the magnitude of the frictional force. So your frictional force is going to be equal to, frictional force is my opposite from 30, so I'm going to use sine. It's going to be 784 sine of 30 degrees, and that turns out to be 392 newtons. Then it says the coefficient between the rock is 0,5. Let's see whether that is true. So there are two different ways of doing it. One is to substitute 392, multiply it by 0,5 and see if you get 678. Sorry, multiply 678 by 0,5. The way I did it was different. I said, let's go and say the frictional force is equal to mu Fn. I'm going to put the frictional force in that I just got, 392. I'm going to say my 678,76, and I find that my mu turns out to be 0,58, which does not equal 0,5. In fact, it's closer to 0,6. We're going to state Newton's third law of motion. Again, pure theory. So for every action, don't forget the word force. There's an opposite but equal reaction, force. Now he is standing on a Newton calibrated scale in a lift. His mass is 75 kilograms. What would the reading on the scale be if the lift were traveling at a constant? Constant means no acceleration, and therefore we have got a mass times by 9,8, nothing weird happening. It's as if we were standing on solid ground, and we get 735, what is it? I think it was just 735 newtons. What would the reading on the scale be if the lift was accelerating upwards? If I pull off upwards, I feel heavier. So I'm going to take 735 and I'm going to add 75 times 0,75, and the reading on the scale will be 791,25 newtons. Tabello enters this lift on the ground floor of a building, and after traveling non-stop gets out on the 10th floor. Which of the following graphs best shows how the resultant force on Tabello varies while she is in the lift? So the first thing is she's getting in on the ground floor. She's going to feel heavy. Then she's going to suddenly get to normal. Then she will feel light. So the resultant force on her to feel heavy needs to get bigger first. So this one gets bigger first, and this one gets bigger first. Before she can feel normal, she has to unheavify herself. Oh dear, that one doesn't unheavify herself. Then she feels normal for a bit. Then she feels heavy in the opposite direction, which is light. And then as the lift stops, she gets to a normal position again. Motor car starts at rest and accelerates uniformly. We have got A, B, C, and D. They are 70 meters apart. When the car is opposite A, a stopwatch is started. At B, it reads 4 seconds. At C, it reads 7 seconds. So that's only 3 seconds. Determine the average velocity, and you should know this from last year. Velocity is equal to displacement over time. 70 divided by 4. Nothing difficult in that at all. And it should be 17,5 meters per second. When is that true? At 2 seconds. Then let's look at the next little block. V is equal to displacement over time. 70 divided by 3, which is equal to 23,33 meters per second. When is that true? In the midpoint, which is 4 plus 1.5, 1.5, so at 5.5 seconds. Now when I have to calculate acceleration, acceleration is equal to change in velocity over change in time. So that is equal to 23,33 minus 17,5 divided by 5,5 minus 2, and I land up with 1,67 meters per second squared.